Yes. So,
So, where I left off, so we kind of skimmed through the first chapter. I didn't read the first chapter by myself yet, so I don't know. We
well, it
could
doesn't
go
it
through and do
doesn't
some
matter.
exercises.
It doesn't matter.
Uh,
It's like you said you wanted to, but
yeah, I did. I did.
but I,
But that's
I,
okay. We can move on and we can
yeah,
go
I mean,
back.
you could still do it. I just don't think it's bad, I guess, if we just do it because it really is. I mean, we started doing it, what the exact same thing that I was suggesting
Yeah.
that we do. So maybe, let's see, where did we actually?
So we were like at, I mean, we were at the end and we were just at the exercises.
I think I kind of burned through some stuff though, right? Like really fast.
Yeah. You skimmed through some
But there's a
stuff.
lot of exercise. I mean, if you look here, there's a bunch. I don't know. Did we go to the end?
Yeah,
Is that what we did?
yeah.
Or did we start doing these? I think we did
I think,
these. Yeah.
yeah, we kind, yeah, we did, but we
That
skimmed to the end until the exercises. We did get to the end. So
okay.
yeah,
Did
I'm down
we go
to do
through
it.
the summary then? There's a summary here. I don't
Uh,
remember. Maybe we did. I don't remember.
yeah, I thought we did, but
All right. So let's just if that's the case, then let's just go through the summary and then we'll just do the exercise. Is that all right?
yeah.
Okay.
Uh,
What?
no, I was just gonna say, yeah, this was I was kind of just I was kind of getting the whole thing, and I could get to the answer, but I was like struggling a bit because it's just a different
It
way of
just
thinking.
takes practice. It's
So I
not.
need
It's not.
yeah
Yeah. It's
I
not
need
a. You know what it's like. It's like if we were doing a foreign language, for example, and then
yeah
you're like,
exactly
well, I've got to
exactly.
convert it into English first, and then see if it makes sense. It's like, yeah, but then you get to the point where you just read it for
Yeah,
what it is,
but
and yeah.
that's why I gotta actually I gotta like go and just do the problems because I can tell very much that this is something that you do a bunch of the problems and then you obviously start to get it. It's not something you
Yeah.
can just read and then move on. I feel like you
No,
need
no,
to
no, no,
actually
no.
do it.
You gotta
You know?
do it, and or you gotta
Yeah.
think it through, and that's what we're gonna do, and you can obviously go back and do it. I mean, the benefit here is you get a whole new world opens up for you at
Yeah.
your job, not just your job, but all like the even the side projects that you actually, especially in our particular areas of interest. There's a
Yeah.
whole.
Yeah.
It really becomes useful, and I'm just very surprised that people don't take data scientists and say, okay, data scientists, forget about object oriented stuff. In fact, you probably just don't even want to pay attention to that. Like I do because I care about like
Well,
software itself, right? And I want to build bigger applications and stuff. But for data scientists, I have people who are going to do machine learning and stuff like that. You and I obviously know the problems that they don't that they not knowing things about programming and algorithms and stuff cause, right? That they have to know something. It's just that I think that they take the exact wrong place and they go toward like standard computer science
yeah.
when
Yeah.
they really should just go
Well, they're
toward.
also just math oriented people, right?
Right,
Like
right,
data scientists are
right.
math oriented, right? So,
So why not
um,
take the
yeah,
more math
I hear.
oriented approach, right? And have like
Yeah,
the total computational equivalent paradigm, but in a mathematical one. And it just
yep,
surprises me. Like Siva can go his whole career and never really, and he'll be limited.
yeah,
He'll have a ceiling, but he never has to go and learn Haskell, right? He can go his whole life and never go there, and
yeah,
he'll definitely be limited. He will definitely not be the best of the best, but he can do it. On the data scientist side, I mean, I almost don't understand. Like you almost you're going to run into like lots of problems if you don't take one of the approaches and learn like some
yeah,
sort of computer science. And it just seems to me that this is the fastest, most efficient way. Plus, you get the
yeah.
benefit of
Well,
knowing a real one.
yeah. 2 seconds before we jump in, we are streaming, right? Is that
Yes.
why? Oh, yeah, okay. So data science, obviously has blown up to a new level like the past 10 years, right? And there's still a lot of optimizing that can be done, and a lot of data science teams aren't organized or structured as perfectly as they could be, just because it's a new field. And I think you shared a video with me a while ago about why functional programming people don't adopt it more. And it was and they an hour like video. It was very great, but the conclusion was basically like, maybe we just haven't optimized enough yet, right? Maybe we're just not there, like in human history. And we'll get there. So maybe a similar thing with data science as well. I thought that was an interesting point.
Yeah. That video was I forgot the Richard something. The guy is like I want to call him the number 2 guy that works on the Elm programming language.
Okay.
Yeah, so
Cool.
he was a JavaScript guy, and Elm is a lot like Haskell, right? Elm is like the web. It's like if you took Haskell and tried to put it into the web. I mean, that's a very simplistic way to look at it, but it is kind of like that. The syntaxes and the ideas are extremely similar. One of the main differences Elm is, as far as I know, is transpiles. So I don't think it has its own compiler. I could be wrong about that though. It's been a while. Elm is definitely something I'd want to get into, but that's another thing, Shane. When you learn this stuff well enough, when you build a front end, you can just build it in something like Elm. Or you can build it in JavaScript and then add pieces of Elm. I mean, I might even start doing that for, like, when we do our unit test stuff. I might start putting that in there just because it adds the typed stuff that really helps stuff like it actually gets rid of some of the unit testing. So that's another thing Galil and I are talking a lot about because we're working on some F# stuff. And we found out that when you can pattern match with types, that totally frees up a lot of unit testing you would have to do.
Yeah.
It's kind of impressive, actually.
Yeah, for sure.
All right, let's go through this summary, and then let's do some of the exercises, and then that'll be it. All right, so this chapter was really about introducing Lambda calculus itself, which is a foundation for pretty much every programming language, but mostly, for sure, like the pure
Functional.
ones. Sorry, I meant functional programming language, but most specifically the pure ones like Haskell and Elm, right? Those ones are pure functional languages, and
they define the difference between pure and not pure, but then they said we'll get more into it later. This idea of purity. What's the
let me see if it's in here. If not, I'll say it. I'll say what my interpretation of it. Yeah, I don't. Okay, I don't see it, but first of all, it has to fulfill everything that's in here. That's the first thing. But the second thing is that I think the main thing about a pure functional language is that it's what is a pure function, right? So a pure function is something that when you give it an input,
side effects.
Has no side effects, which is a fancy way of saying that if you give it something, it has to only operate on that data, and then it has to produce a consistent result. So a given input should always produce the same output. And the side effect part is that it can't do other things, right?
Okay.
It just transforms that data and does something to it, but it doesn't print to the screen. It doesn't try to hit databases. It doesn't do things where the results.
One input, one output. That's it. No other logic or any other results are coming out of it.
Right. So this becomes questionable when you talk about dependencies and I/O bound stuff. All sorts of stuff. Reading, writing to sockets. Lots of things, and obviously in a practical world, you need solutions for those things, and through monads and some other things, functional languages have that. Those are the tools they use to attack those kinds of things, as opposed to directly applying the side effects. So they can keep their functions pure, and then write composition.
It's interesting because the things in imperative languages that are super simple, like just like printing to the screen or something like that, that actually ends up becoming like a that's like a side effect. So that's more difficult because that's just not like the foundation of like right that's more difficult in these languages.
Yeah,
But
yeah.
they're solved
I
completely.
mean, when you say more difficult, right? Like,
Mm.
what makes it happen in those languages that it's easy? Like, what are you doing that makes it easy? Let me ask that question.
Yeah. Um, I was just purely referring to it's just like a simple line of code.
Okay, but
Um,
these languages have abstracted those parts away to make it a simple line of code.
yeah, so it's you still I imagine
Now,
have
that
those.
like so in Haskell I can print to the screen, but the problem becomes, what if I want a function that like does some stuff to the data, then prints out what's there, and then keeps operating on the data? That's a simple thing. For
Yeah.
so that's really the issue, because that's a simple thing to do in like Python or an imperative language. It's not a simple thing to do in a pure functional language, because all of a sudden what you're doing is you're piping data and you're manipulating the data, and then you're saying, wait, stop. Let's actually
Yeah,
just look
yeah,
at the
yeah,
data.
yeah.
Let's look at the data, and then, okay, go again. Right? You're
No.
doing a procedural imperative
Okay, I
based.
see. If it was just printing to the screen, that's fine. But like
Well,
now that
it's
you
fine, but it's still the concept of a side effect, because
yeah,
there is no just printing to the screen really when you think about it, because what's happening is you're sending, then if you say I'm just going to print to the screen, you have a function that takes in an input, prints it to the screen, but then it needs to return something. So you're
hmm
still taking the data and piping it, telling it to stop its execution, look at it, and then come out, right? So the way they
yeah,
get around that is they wrap like a command and the data itself. So you pipe this command and the data.
yeah,
The command passes off to the runtime function and returns, whatever the command result is. So it actually ends up printing to the screen, but it's all wrapped into this pure monad, which is like handling results or no results, like results and errors at the same time.
yeah.
It's hard to explain when we'll see it,
Yeah, well, we'll see it. Yeah, but
but
okay.
that's a very
Let's,
common pattern. Like the most common, like here's a very good example of a side effect problem, right? Or not. Sorry. That's an example of a side effect problem, right? But here's another example that's not a side effect problem, but it is a problem of pure function, and that would be if I wanted a random uniform or a random normal variable or something like
yeah,
that. Now
yeah.
you have a problem, because
Well,
now you're saying that,
because you're breaking your consistency rule
right, the
that you kind
input
of mentioned.
output consistency rule.
Yeah,
In effect, it does the almost the same thing that I just said, where you pass a command off to the runtime, and the result that comes back is a result success wrapper.
yeah.
So you end up having the same type.
But yeah, but even like just based on our naive understanding of like probabilistic programming, it's which seems to be different than imperative or functional. Um, maybe it's more appropriate when you're breaking these consistency rules and you want some sort of distribution, whether it's random, uniform, or anything else, to know to use like those languages.
Maybe, except what I just described is that you're not breaking the consistency rule. Right? So, like, if you were to do it without doing what I said, it would break the pure functionality. But the way they do it makes, like, with a wrapper, allows them to not break the consistency rule.
Yeah, yeah, I understand that they have a way of. I mean,
I mean,
yeah,
they're
imperative
literally keeping
languages
it
do
pure. They
too.
are actually keeping it pure. And actually, you know what? It's like the pattern that I put in JavaScript in the Postman thing. It's like
Yeah, yeah,
it's like doing that. Whereas we have this thing, and it saves it to a success and an error variable
yeah,
at the same time, right? So that the return value is always a tuple or a tuple of those two values,
yeah.
right? So it's like passing the command and the. So
So
now, no
okay,
matter what happens,
so that's a very common structure in
yes,
functional language.
yes,
Okay, so I'm
yes.
happy. I'm going to learn about that too because
Yes.
that was
That's why I
interesting.
was
I
trying
said
to tell you when I
JavaScript
wrote
too.
it. I was like, well, it's not. You're like, I haven't seen this before, and I'm like, yeah, it's actually just a pattern that I've seen, not really in JavaScript, but in other languages. And the good news there is you can apply those patterns that you learned
Yeah.
here into any language that you're using. Well,
Yeah, yeah,
any
yeah.
one that is dynamic like Python or JavaScript or something like that. But pretty much
Sure.
any language. That's the beautiful part about this. That's why it's crazy to me not to learn this stuff.
Yeah, yeah. I mean, I could tell it was like an interesting structure. That's why I asked about it.
All right, so let's just go
All right,
through
cool.
this. The main points you should take away
Okay.
is that functional programming itself is based on expressions that include variables or constant values, expressions combined with other expressions and functions. Wait, is expressions that include variables or constant values based on expressions that include variables or constant values, comma expressions combined with other expressions and functions. So basically, it's just expressions or functions, which have some sort of value variables or constants, right, as
Okay.
arguments and stuff. Um, they have a head and a body. So if you remember the lambda whatever dot whatever, the one before the dot
Yeah.
is the head, and the one after the dot is the body. They can
Okay.
be applied to arguments, and the applications we learn are beta application, alpha equivalence, and reduced or evaluated to a final result.
Okay.
Variables may be bound in the function declaration, and every time a bound variable shows up in the function, it has the same value. So it can't be mutated.
Okay.
That's another thing about pure function is that you're not mutating this stuff. All
Okay.
functions take one argument and return one result. That can be seen in currying.
Yep.
Functions are a map. This is just actually a mathematical definition of a function, although pretty much all of them are.
Yeah. Inputs
Functions
to
are a
out.
mapping of a set of inputs to a set of outputs. Given the same input, they always return the same result. Vertical line
Okay.
test if you're teaching kids. These all things apply to Haskell as they do any purely functional language because semantically Haskell is a lambda calculus. Actually, Haskell is a typed lambda calculus, and Idris is a dependently typed lambda calculus. More on types later, with a lot of surface level decoration sprinkled on top to make it easier for humans to write, but the semantics of the core language are the same as lambda calculus. That is, the meaning of Haskell programs is centered around evaluating expressions rather than executing instructions. And actually, a lot of that
Yeah.
gets seen in the fact that the idea that it is far more declarative than it is imperative. Oh, which is an abstracted way to say, oh, go do this, right? This is what I want done,
Yeah.
versus this is how I want you to do something.
Yeah. Yeah. Yeah.
Haskell has a way to execute instructions too. We will still be making reference to the lambda calculus when we come to later to the apparently very complex topics. Function composition, monads, parser combinators, etc. Don't worry if you don't know these words yet. If you understood this chapter, you have the foundation you need to understand them all. It's pretty impressive because they just taught you lambda calculus and saying that's basically what the programming language is. Think of learning any other programming language. You have to learn like these very specific patterns to the language. And they're saying,
Yeah.
no, 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 you don't need that here. You just need to understand like the
Well,
concept.
yeah. Well, it's very hard to teach a language like the foundation of any like imperative language or whatever, right? Like you start off with like basic commands, but you don't have the foundation for a long time.
Right,
So,
unless you start with like assembly and machine code, but who wants to
well,
do that?
yeah,
Right,
exactly.
because you're telling it about how to do it. So the how to do
Yeah,
it is all based on with memory registers, how you create for loops and
yeah,
infinite loops, how you have an end command go back up to the earlier on in the ROM command, address registers. It just becomes like, who wants that? And then you say,
yeah,
oh,
yeah,
we'll make a stack, and you're talking about tools that were built on the how to, versus like the algorithmic,
sure, sure. So it's okay, okay, cool.
All right, so we're going to do the following exercises differently than what you'll see in the rest of the book. Unlike the subsequent chapters here, we provide some answers, explanations for the questions below. They do that because they really feel like you need to
Okay,
actually understand combinators.
and
Determine whether each of the following functions are combinators or not. So combinators, if you remember, we'll just review real quick. It means that there's something in the head that doesn't show up in the body. So
something in
let's
the head that
actually,
doesn't show up in the body.
yeah. A combinator is a lambda term with no free variables.
Oh no, free there. Okay. Yeah. Okay.
Oh, sorry. It's the exact opposite of what I had just said. One that shows up in the head that doesn't show up in the body is not a combinator. Ones that do like stick to the rule are combinators. So these are combinators. This is a combinator, but this is not.
Oh, okay.
So wait. No. That's wrong. Sorry.
Uh,
These are all combinators because the variables that are in the body are in the head.
show up in the head.
Right.
Yeah.
So this one is not because the x is
Okay.
nowhere. This one is not because of the z. So z is
Yeah,
a
yeah.
free variable, right?
Okay, let's see. Yep,
Uh,
it's a free. I remember that.
Divergence, by the way, I don't think we went over this.
Yeah, I don't remember combinators.
Or
I remember free
divergence.
variables though.
So
I don't
actually,
remember
this is
divergence.
yeah. So okay, so you understand combinators? You feel like?
Yeah. Those
All right.
seem.
So let's talk about divergence real quick. So, not all reducible lambda terms reduce to a normal form. This isn't because they're, and divergence means what you think it means, okay? So, this isn't because they're already fully reduced, but it's because they diverge. Divergence here means that the reduction process never terminates or ends. Reducing terms should ordinarily converge to beta normal form. So, you can like reduce the lambda, reduce till you get the simplest version.
Yeah.
This one can never reduce. It
It'll
just
never. Yeah.
it either gets
Never.
bigger, yeah, it either gets bigger or it stays the same.
Yeah.
Here's an example of a lambda term called omega
Omega.
that diverges. I don't know why they call it omega, but okay.
Okay.
So let's think about what would happen here.
Okay. And real quick, last thing. It's so less left like associative.
Mhm.
That's what it's called, right?
Left associativity, yeah. Yeah, I mean you take the leftmost set of parentheses, so something like this, and then you
Yeah.
beta reduce it. So if there's stuff inside of it that, other lambdas and stuff that need to be reduced, you do that. And then once that's beta reduced all the way, then you start moving outside the parentheses to the right.
Okay.
All right. So let's start here. These are beta reduced, meaning it just says lambda x is 2x's, right? X
Yeah.
applied to x. So what's going to happen? What do you think is going to happen?
So, do you just end up with just X or something?
Okay. So let's take this.
Uh-huh.
So we're going to apply this thing right here, the second one,
Yeah. Oh,
to
yeah,
this
yeah,
one.
yeah.
So this
Yeah.
whole second set of parentheses becomes this x,
Yeah.
and then you get two more of them, just like we
Then you
have
get
here.
two more.
Just like we have here.
Okay.
So it becomes already what we have, right? So this whole expression
Two
goes in.
X's.
No, it
Or-
becomes what you see here, right? So
Oh.
so we're taking this function. This is a function.
Yeah.
We're taking the function and applying the. So this lambda right here says take an argument x and make
Yeah.
two of them.
Two of them. Yeah.
So we're taking this function and then
Yeah.
making two of
That's
them.
Yeah. Oh, you're making two of that function, and then
Yes.
okay, and then
So
you
then we
actually
end up where we
getting
started.
the exact same result here.
Right.
Okay, yeah.
So
I
it
see,
doesn't.
I see.
So you can see. So they replace x with
Yeah.
the function and then make two of
Yeah.
them, and that gives you two of them again. So
Yeah,
it never
yeah,
process never
yeah.
ends. In this
Okay,
case,
good.
that omega diverges. There's
Yeah.
other ways they
It's-
diverge. Like if I had three of them, then it would just get bigger,
Yeah. It would just yeah.
right?
It just would like diverge quicker or something.
I guess. Like if I put
Or
a
something like that.
basically if I put a third x in here, that
Yeah.
would just cause the whole situation because then it would be three of them.
Oh,
and
then you get
that
three.
one would be two of
But
them.
it keeps. Yeah. Okay.
You know what I mean? If I made each of these three, that it would just
Yeah.
diverge. Okay, so let's go to the exercises. So the combinators. Which ones are combinators?
Okay. Cool. So the first one's not a combinator.
So
the
you
second
just have to look at the bodies and see if it has any free variables.
So the second one, Z, is a free variable, right? So that's a combinator.
Right, right.
Or wait, did I get the definitions backwards?
No, you're right. If there are free
Okay.
variables in the body,
It's a combinator.
it's a combinator.
Then it's a combinator. Yep. So that's not a combinator. It could be X, Y, Z. X, Y, Z. That 4 is not a combinator. X, Y, Z. 5's a combinator.
No, 5. So 3 and 4 are combinate. So 1, 3, and 4 are the ones that have no
Oh,
free
oh, no,
variables.
no free variables are common years. Yes. So okay, I
So
got it.
2 and
So
5
two
are
and
not.
five are not common years
So
because they both have Z.
let's look at the answers. So oh, I didn't. I don't. I guess we didn't do the equivalence ones, but so yes. So 1, 3, and 5. Yes, yes.
Yeah.
Sorry, 1, 3, and 4. Yes, and then 2 and 5 are not.
Okay. Yeah, I just had
Not.
them backwards. So
Yeah.
no free variable is common
I
here.
guess I skipped. I didn't see the equivalence ones though. Just go here and it's
I
right on.
think we did them at
I
first.
think
We did
that's what
them
the
last
ones we
time.
did. Yeah, yeah,
Yeah,
yeah.
those are the ones we did.
Okay. So normal form or diverge. So you get them into normal. I said
Yeah.
beta reduction, but you get them to normal form. So normal form or divergence.
Yeah. So now you're just gonna have for one, you're just gonna have 3x, but you're not applying it to like any other function. So there's no more like. So that's just it. So
It's in
that would
normal.
be
It's in
normal.
normal form. Yeah.
Yeah.
What about this one?
So this is gonna diverge. It's the same as the one before.
It's equivalent, right? These are alpha.
Yeah.
This is what alpha equivalence is. These two
Yeah.
are the same thing. All right,
So that's
3.
gonna. And then this is normal.
Right. I mean, the
Um,
only thing you could say is you'll get 3 Z's, but
so is that alpha equivalent to? Oh no, to one? No, it's not because one's just a function. You're not
well, you would
applying
beta
anything to
reduce this. This is called beta reduce, which we're going to do next. You beta reduce this to ZZZ. I don't know why they did that one. Let's see what they say. So, okay, so this doesn't diverge, has no further reduction steps. If it had been applied to itself, it would diverge, but by itself it does not, as it's already in
Yeah.
normal form. This one diverges. It never. This is the omega term. Its alpha equivalent is what you saw before. This one doesn't diverge, but it reduces to ZZZ. I mean, I don't know why they
Yeah.
did that exactly, but whatever.
So it's never possible to diverge if you only have one function? Is that true here?
Yeah, I
'Cause
mean,
you
it doesn't.
applying-
It can't.
It's
It
already.
can't diverge. I mean, not in
Yeah.
a pure function, not in a lambda function, right?
Yeah.
It's not doing anything.
Yep.
It's like potential energy, I guess.
Yeah.
Um,
Okay. Cool.
Evaluate that is beta reduce each of these to normal form. We strongly
Strong.
recommend writing them out on paper. We don't have to write them out on paper if you can do these
Yeah.
in
Let's
your
just
head.
we can just slowly go over them and just
Okay.
see
So-
what I'm right if I'm right or not here.
So number one.
Um. So number one. So do we? I forget. I feel like we were starting from like, even though it's left associative, you start from like the right, and or you? Okay. So do you?
There's
do
no
you
way
apply,
to do that.
Okay.
So in other words,
So do
just
I apply
ignore
ZZ to
ignore
the-
everything after the z's for now.
Okay. So that's kind of what I thought. Okay. Cool. Okay. So we're applying ZZ to this function. ABC, and then we get a CBA out of it. But it's taking in like 3 like expressions or arguments, and we're only giving it like these 2.
Okay.
So, but it looks like it just kind of like reverses them. So maybe you're just
okay.
left with ZZ.
What happened? Wait a
Right.
minute. So the
I'm kinda
first
confused,
the first
yeah.
z, the first z. Let's just do one argument at a time.
Yeah.
So the first z becomes the a.
Okay.
So then you have lambda. So remember, by the way, lambda a b c dot cba is the equivalent
it's
of lambda
of 3
a,
lambda,
lambda
right.
b, lambda
Yeah,
c
yeah.
dot
Forgot
cb.
about that actually.
Right. So, but either
Okay.
way, if you need that, you could write that out. But if you don't, then you can say, okay, the z becomes the a,
Yeah.
and then it replaces it here and gets rid of
Yeah.
it in the head. So then we have lambda
yeah.
b.
So then you just have. Okay.
Then we have
you have lambda BC, and then you have the Z.
we have cbz,
CBZ.
right? The a becomes the z.
Yeah.
Z becomes the a, I should say. And then the
Okay.
second one. So now we have
Then
lambda.
we just apply that to the B.
Okay. So then
And
we
then we'll
apply
have
it to the b.
then we'll have C. We'll have lambda C. Or no, we'll just
Yeah,
have C.
yeah, that's correct. No. Yeah,
Okay,
that you were
lambda-
correct.
Okay, lambda c
Uh-huh.
zz.
Lambda c dot czz, right?
Yeah.
Then we apply this. Now we've
Lambda
gotten
c
rid of the
dot
z's. Then we
czz.
apply
Oh
this
yeah, yeah,
function
yeah, yeah.
here.
Okay, okay.
So that
Uh,
becomes the c.
okay. Yeah, 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 yeah. So then you have lambda c. So and then zzz. Um.
No, no,
So you
not z, not
no no no.
z, not zzz. There's only
No.
two z's.
Oh, it's lambda c dot czz
Yes.
is what we have for
So
the
then
first one.
this becomes the c,
Yes, yes,
and
yes.
that means you're applying this to the zz, right? Because this becomes the
Yes.
c, and now you
Yes.
have
Yes.
this zz. And so what happens when
Yes.
you apply this last thing to zz?
So then you're just gonna get lambda. Uh, you're just gonna get lambda v. Uh, I might need to do these steps
No, no,
again.
you don't. You don't. You don't. The W and the V each become z's.
The w and the v each becomes these.
If I
Uh,
apply this to zz,
yeah,
if I apply this
yeah, yeah,
if I apply this to zz, the W and the V each become z's, and then I'm just left with the W,
yeah, yeah.
which
Oh,
is a Z.
so you just have a z.
Right.
Okay, okay.
So let's go down and
Geez.
make
Yeah,
sure.
that was a hard one. Okay.
Here we go. All right. There it is, right here.
Okay. So let
So
me.
so this is the part that I
Yeah,
forgot.
that was the first step that you. Yeah, I forgot about that.
Yeah, they did one Z at a time. See, they got rid of the A,
Yeah,
and then they got rid of the B, and this is where we were. And then we
yeah.
had this, and then this
Yeah,
becomes the C,
yeah,
applied to those Z's, applied to one at a time, right? And that's why the currying, and then that becomes the W, and now you have lambda V dot Z, and then applied to a Z, which just really just gets rid of the head because
yeah. Between 4 and 5 was hard for me to keep in my head. Um,
that's the easiest part. This is the hard part, I think. But yeah, I think this is because this is just saying I'm applying something. So you're really just like taking this and applying the ZZ arguments. But yeah,
yeah.
I
So
mean,
then,
to each
okay.
his
So
own.
then they got. Wait, let me just look at it real quick. So then they have lambda w, lambda v. Yeah, because they just applied it to the c, and then it's yeah, yeah. I see how it's an easy part now. You just have that, and then zz,
Right.
and then you just apply the z to it.
Yeah, but since there's
So
no V in the body, it just gets rid of the V.
it just gets rid of the
It's
v.
like having
Yeah, yeah.
function of V return
And then
five.
you get z. Yeah, and then you have lambda v z z, and then then you apply the z to it.
Right. And like I
Uh,
said, it's like saying function of V return 5.
Yeah,
And you didn't even apply the argument at all to anything.
yeah, it doesn't matter because
Doesn't
there's
matter.
there's no v in the body, right?
Right.
So then you're
Exactly.
just
So you're left with this Z. This is the
you're
Z
left with
that's
that
left
z.
with.
Yeah, yeah.
If this was
Okay.
something else, you'd still be left with Z. Okay.
Yeah, it's very simple after seeing it all out, but having it in your head
That
the
is
first time
that
is
is
hard.
exactly what functional programming is. It's like once you understand it, you're like, "Oh my god, why are we doing other things?" Because you're like,
Yeah,
"It is that
yeah.
simple." Come on, people. Like that's for real.
Yeah.
That's for real,
Just
man.
training your brain.
Yeah.
So
Yeah.
okay, so it's the same thing. We're because of left associative, we ignore the b. So then we're applying lambda a to the first function, and then so what's going on here is you have x and then 2 of the second function y.
We'll take it one thing at a time.
Okay.
So this one right here
So we got it
becomes the x.
becomes the x.
So what
So
are you
then
left with after doing
Yeah,
that?
so then you're left with that function, lambda a, and then
Well, not exactly.
y.
You're still
right?
left with the
You're-
lambda y.
You're left with lambda y dot lambda a y y.
Yes. So you're left with lambda y, And now
Yeah.
in the body, you're applying this function AA to the
Yeah.
y's. So we need to do that before we move on, because it's basically like saying lambda y lambda a dot y. No, it's not. It's actually, wait, lambda y lambda a. Oh, it is dot y.
Yeah. Oh, it's
Yes,
like.
yes, yes. It is like doing that. Yes.
Wait, is it the same as saying So is it the same as saying lambda y dot lambda a
Sorry.
y?
Lambda. Wait, it lambda
Or
y? Yes, yes, yes. It is.
it's not the same as saying lambda y dot lambda a dot ayy?
So, actually, I might as well just bring up Haskell if we're gonna do that. So we'll write this out. Stack GHC. This will take a moment. It's kind of fun, right?
Yeah, they're cool. Yeah, I like it.
Okay, I'm gonna write it out
Um,
here. So we'll just say, come on. I'll call this one two. I'll just make up
where you're left with just the function. Oh, you're left. Okay.
I don't know why it's taking so long.
It almost feels like uncomfortable to be so like to be so left field because you can tell that this is like pretty simple stuff.
I know.
But to not be able to do it, like that,
All
that
right.
feels
Well,
weird.
while this is loading up, I don't know why it's taking. This is kind of crazy.
To
But
be struggling
basically,
with this thing simple.
yeah.
Okay.
So, but basically, so the cool thing is, I mean, the thing to keep in mind is like the thing that we were talking about before. I think it was with this one where this is the equivalent to lambda a, lambda b, lambda c.
Yeah.
So if you take this and apply it to the x, you're left with lambda y, lambda a, y, which is if you wanted to reverse that, you would have lambda ya dot y.
Lambda y a dot y.
Right.
Like I understand that. I understand that when you apply this to the x, you end up getting lambda y dot lambda a dot y.
Well, you get lambda y dot lambda a dot a.
Dot ayy.
Yeah,
right?
yeah.
Dot ayy. Okay, cool.
But anyway, I think. Oh my god, this is crazy, dude. I don't know why this is taking this long. But anyway, so the quicker way to do it though is to just say, okay, just put the lambda. Let's put this function in place of this x right here, and then we'll apply these y's to it.
Yeah. So we're applying yy to the lambda a dot a function.
Yes, and what do you get?
So then you just get yy.
Yeah, let me get rid of this because I don't know what that was.
Right.
Yeah, you do, and this is pointless for me to even write at this point because we're almost there. Okay, so now this x is
Then you
gone.
just get yy. So then you just get lambda y dot yy.
Lambda y
Right.
dot y. Right.
Yeah.
And then what
And
do you
then-
get?
And then
okay, so now you
oh,
apply
then we're
it to
applying
B.
b to it. So then you just get bb.
Right.
Or
Yeah.
yes. Wait. Yes. What? Yeah.
See? BB.
Cool.
So yeah, so they did this. I was thinking that you could do lambda y, lambda a, but I don't think you can. I don't think it would work like that. Because it would have to. If you did that, you'd have to like have the a at the end. If you think about it, it wouldn't quite work. Does it work? It doesn't work because this is being applied here. It's not just another.
Yeah.
But anyway, that's just my
Okay. Well, that one was a bit easier. Okay. So what do we got next? Okay. So now, since we're applying the lambda x dot xx to lambda y dot y, that's just like the identity function.
Yeah.
So-
See, now you're
so
getting the
it's
pattern. Now you're like, oh, get rid of that. I don't even need to
so
try
we
it.
have lambda
Yeah.
x dot xx,
Mhm.
and then we're applying. So you're just left with.
Then you're
left
making
with
it
two of
twice.
lambda zq's.
That's it.
Okay.
See why it's worth it to take that first step. Because now you're just like zing, zing, zing. See, there they are.
Okay.
Oh, wait a minute. Ooh, my bad. That's wrong. That's wrong.
Oh no! Wait! I didn't even see the answer. So let me go back and
No, I know
let me just try and
why.
do
I
it.
mean, it was a.
Let me
It
just try
was.
and do it.
It was a. It was yeah. Yeah.
Let me just do it one more time. So then you get the lambda x dot xx, and then now we're applying lambda z dot zq to the to so so you get two of those lambda z dot zq, and then you get lambda z dot zq,
Okay.
and you're applying that to lambda z to that first function,
Uh huh.
and then you end up getting this function q,
So you get this
right?
function applied to Q, right?
Oh, that function applied to q, which is just qq.
Yeah. There you go. That's what it is. That was just a little bit of an oversight.
Oh,
Yeah.
we just like stopped.
QQ. Right. 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 Well, because we weren't thinking like because there's a free variable in there. Really,
Yeah.
that's the whole thing that causes.
Okay.
Okay. So now this one, and it says hint alpha equivalence.
Okay. So then you get lambda z z z. So then you're applying this. So you get two of the last function there.
Yes. Yes.
Um,
Yes. Yes.
so then you get the last function y.
Isn't this
So,
the exact same
isn't
problem
it the
as the
same
one
thing? It's
before it?
y.
Yeah, I think so. I mean, I don't. That would
Well,
be
it's an alpha equivalence, so.
yeah. YY. Yep. Exactly. Yeah. Alpha equivalence meaning the same. Okay. Number 5.
Okay. All right. So lambda y that becomes the x. You're ended up.
Okay.
With
So
lambda.
they're actually trying to cause you a problem.
Yeah, they're trying to because the y's are separate here.
Yeah. Yeah. They're trying to
One,
cause a
one,
scoping
two.
issue here. Yeah.
Yeah,
Yeah.
yeah. All right,
Exactly.
that's all right.
But it is an identity function, so you can get rid of it pretty quick.
Oh yeah. Okay. So then you just end up having your identity function. You have lambda y dot identity function y,
Mm-hmm.
and when you apply y to the identity function, you just get y. So
Right.
so now you're left with lambda y dot y. You apply y to that, and you end up with just y.
Yes.
Is that right?
I believe so. So it's been YY again. Yep. Exactly.
Okay. 6. So then you get 2 of the second function. You apply 2 of the second function. So then you get the second function a. And then which ends up being AA, and then you get AAC.
Yeah. Nice. That was a good one. That one wasn't quick to think through, but you did a good job. AAC. Steps we took. Wait, no, number 7. Whoops. All right. So this one I think is the last one out of these, and then I think that's it. This is the very last one right here.
All right.
Okay.
So you actually just get Z no matter what. Z is basically a constant in that second one, but we still got to apply it. And same thing for the last function too. You get A no matter what. So, okay. So.
And it has some associativity, which is interesting.
Okay. So we're applying this to X, or this counts as X right here. So you end up getting the lambda x z. You end up getting the constant function. You end up getting lambda y z dot the constant function z y z. I'm calling the second one the constant function.
Okay.
So you end up getting lambda y z dot the constant function z y z. Oh boy, dude, I might need a paper for this one. This one's hard in my head.
I think it's easier than you think. It just looks bad. Because what you're doing is if you're replacing this one right here Sorry, the constant
Yeah.
function that you're saying. If you're replacing that with the x in the body,
Yeah, I am.
and then apply, so what you're applying z to it. So what do you get
Yeah,
when
so
you
you just
apply
end
z
up
to
get.
this?
Oh, so you end up just getting z.
Right. So now you have
Right.
z y z.
That
You have
constant z.
lambda yz, z y z, and now you've gotten rid of this,
Oh,
and now
lambda
you're applying
yz. You have lambda yz dot zyz, and then you apply
that to
lambda,
y.
which is just a constant as
So now you
well.
have z. That becomes your new y. So z, and then inside here you have this other constant function that will give you an a, but now you're applying
Yeah.
this to z. So that just gives you an a. So
Yeah.
you have your z and your a. So now you
Yeah.
have lambda z dot z a.
Oh, lambda z dot za. Are we applying? We're not applying anything. That's the whole.
Because
that's
think
the
about
end?
it. Think about it. Let's
Yeah.
step back for a second. This thing got applied
Yeah.
got applied to a z, right?
Yes.
This
then you ended
thing also got applied to a z. So
Yes.
so let's apply each one of them to a z. So this get applied to a z gives us a z. This one
Yeah.
gives us an a.
It's got an
So
a.
these two become a z.
Yeah. Then you have a z.
These two become an a, and the x and the
Oh.
y are gone. So but you still have lambda z.
Yeah, the lambda z still. You haven't applied any. Yeah, so you're still left with that function. So then you just end up getting lambda z.
But it's a
dot
different.
ZA.
It's a different. The problem is this is a different. I think this is a
It's a
different.
different
z
z.
than
Yeah,
this
it's a
one.
different z. Well, is it though? Because it's a con. Yeah, it. No, is it though?
I don't know. I guess it's the same. Maybe it's the same. I don't
It's
know.
probably the same, I would think. Cause
So anyway, the only well, I think though it is different.
no, it is
yes,
different.
yes,
in the
it's
first
different
one.
than this one. Yeah, this one is
In the first one,
scoped
it's
to
just an
there.
argument.
Right.
Yeah, it's just that.
So
argument.
you're not actually. So you're gonna get this z. So let's call this one z1 and this one z2. So you're gonna
Yeah.
get
So you end up-
z2a.
Yeah, but you end up getting lambda z1 dot z2a.
Right. All right. Let's see what they did, and then they have steps down there. Let me just see if they ended up with a function. They dude, they did.
Ah, there we go. They did the exact same thing.
Yeah.
Okay, great. Great.
All right. They did that for scoping reasons. One's bound by the head. Second is a
Oh,
free
yes, they're
variable.
just showing
So
us-
it's exactly
yeah,
what we
yeah,
did.
yeah.
We just called. Where is it? They left it as z.
Called it z2.
Yeah, we called it z2, and we called this one z1.
Yeah.
So we still called it z1, but we had z2 there.
Yep.
That's the
Yep.
only
So we had
difference.
the same thing.
And then they just kind of do it. So I don't think we need to do it because we did it right. And this is the very last section until they get into Haskell, and we'll stop there. Definitions. Lambda in lambda calculus is the Greek letter lambda used to introduce or abstract arguments for binding. A lambda abstraction is an anonymous function or a lambda term, so you'll see that in lots of programming languages. They'll call it an anonymous function. Python calls them lambdas terms.
Lambda.
The head of the expression abstracts out the term body there. We can apply it to any x and recompute the different results, which we apply to the lambda. Application is applying it, binding the parameter to a concrete argument. The argument is what is applied to. Computations are performed by applying arguments until you run out of applications. This example reduces to 1, as this identity is applied to the value 1. Just kicks the 1 out. This consumes it. We reduce the amount of structure with which we start. Lambda calculus is a formal system for expressing programs in terms of abstraction and application. Normal order is common evaluation strategy in lambda calculi. Normal order means evaluating the leftmost, outermost lambdas first. Evaluating nested terms after you've run out of arguments to apply. Normal order isn't how Haskell code is evaluated. Haskell's evaluation strategy is called
Call by need.
call by need. Instead, we'll explain this later. Answer the evaluation exercises are in normal order. Follow-up resources if you want to see them. Introduction to Lambda Calculus. I've read one of these too. I don't know which one. Okay, that's it. And then the next chapter is installing Haskell. So you should probably actually definitely do
Yeah, I
that.
should
I
go
would say you
through
don't
them.
need to do any more of the Lambda Calculus because that's pretty much done. We'll
Yeah.
reference it. We'll think about it. We'll talk about it that way. But I would say you should definitely do this
Yeah, get Haskell.
chapter.
Yeah, man, that was fun. Definitely got better at it, just even in that session. So
Yeah, you did.
That's
Even
something.
in one session, and even within the session, yeah.
Yeah, exactly.
I would say definitely do this chapter. It looks like
Yeah.
you can easily do this. So you just install it and you just start. They're really just toying around
Yeah.
into the repo,
Yeah.
learning a little bit about Haskell itself.
Some of the
Is
syntax and stuff.
how to run a file, the syntax,
Yeah.
just the basic stuff, how modules work.
Yeah, I'll go through.
I don't
I'll
know
go
how
through and set this
long
up.
it is, so I'm just kind of trying to quickly look and see if it makes sense for you to do the whole thing on your own. I think it does actually. I think it definitely does. There's nothing to really talk about. I'm just trying to get there. I think it's probably close to the end of it. Yeah, it seems. Oh yeah, this operator. That is interesting.
Well, at
Haskell
least
doesn't
get
even
the
have a
beginning
piping
of it
operator
done.
actually. What's that?
I'll at least get the beginning of this chapter done. I mean, it looks. I mean, maybe I'll get through the whole thing. It doesn't. It looks like pretty simple. But it also
It
looks
is simple. It is definitely simple. You have to go through it though because it's not as unusual as the lambda calculus one if you've never seen it.
Yeah, but I still need to know all of it.
But you still need to understand what you're about to see, right? You need to
Yeah.
understand the syntax. You'll connect with it a lot quicker.
Yeah, I need. Yeah,
Um,
yeah, yeah. Okay, cool. Yeah, well, I'll do that then, and I'll let you know where I'm at in that chapter. It looked decently long, but that's okay.
No, just do the.
Um,
Yeah, I think you can totally do it on your own. If you have any questions, obviously ask me. But I think the next time we should try to do strings.
yeah.
That makes
Okay, sounds good.
sense to me.
All right.
See,
That sounds
you
good.
can
Yeah, that
literally
was.
write this in Haskell, so it's not like you can't do it.
Yeah, yeah.
you know.
Yeah, that was a little fun, man. I'm not gonna lie. I like those
Awesome.
those problems.
Well, then
not
you will
gonna-
like functional programming because it is a lot like that. I'm ending the stream, by the way.
All right, cool.